law states that when light passes through materials with two different refractive indices, n1 and n2, then light bends or refracts at the interface according to the equation n1 sine theta 1 equals n2 sine theta 2, where theta 1 and theta 2 are the angles between the light ray and the normal or perpendicular line to the interface. Here's an example of Snell's law. We have a laser, and it's shining light on some glass, and the incoming laser beam bends or refracts when it reaches the air-glass interface, because air and glass have two different refractive indices. Air has a refractive index of about 1, and glass about 1.5. Now, Fermat's principle states that when light travels between 2 points, it takes the path that requires the least amount of time. Here we're going to use Fermat's principle to derive Snell's law. So let's consider 2 points A and B in two different materials. A is in a blue material through which light travels at speed v1, while B is in a yellow material through which light travels at speed v2. Now you might think that if light is traveling from A to B, then the fastest path for it to take would be a direct line between them. But it turns out that if v1 is bigger than v2, so light's traveling faster through the blue material, it makes sense for most of the path to be in the blue region, where light is traveling faster. That'll minimize the time spent in the travel. And if v2 is bigger than v1, then it makes similar sense that most of the path should be in the yellow region, where light travels faster. Now, would it be possible to have a curved path like this? Well, no, because in the blue region, if light is traveling at speed v1 the entire time in the blue region, then a straight line from A to that point on the interface would require less time. So the general shape that we're going to have for the path of the light between A and B through these two materials is going to be a straight line in the blue region and a straight line in the yellow region, but together they'll form a kink at the interface. What we want to know is where this point on the interface will be that minimizes the total transit time. So let's label some sides here. Let's put some math into this. So the point A, let's say, is a distance x from the interface. And the point B is a distance y from the interface. And let's also suppose that the total horizontal distance between A and B is length d. And now let's label the distance between the horizontal distance between A and that point on the interface where the light hits the interface as a length z. And then the corresponding horizontal distance between B and that point on the interface is d minus z. Okay, and we can now use the Pythagorean theorem to find the lengths of the paths in the blue and yellow regions of the light. So we have a right triangle in the blue region, and so the length of the path in the blue region is the square root of x squared plus z squared, and the length of the path in the yellow region is the square root of y squared plus d minus z squared. So our goal here is to find length z that minimizes the travel time between A and B. We're trying to find the point on the interface that minimizes the time that it takes for light to travel from A to B. Now let's recall that speed is equal to distance over time, and so time is equal to distance over speed. Now we can find the time it takes for light to travel through the blue region by taking the distance that light travels in the blue region divided by the speed at which light travels in the blue region, using time equals distance over speed. So t1, the time it takes for light to travel through the blue region, is the square root of x squared plus z squared, the distance, divided by v1, the speed of light in the blue region. And similarly, t2, the time it takes for light to travel through the yellow region, is the square root of y squared plus d minus z squared, the distance, over v2, the speed. And so the total time it takes for light to travel from A to B along this path is t1 plus t2, or the square root of x squared plus z squared over v1, plus the square root of y squared plus d minus z squared over v2. So here's an expression for the total time it takes for light to travel from A to B. And what we're trying to do is minimize this time. We're trying to find z that minimizes the time it takes for light to travel from point A to point B. In other words, we're taking the derivative of the total time with respect to z and setting it equal to 0 to find the minimum. And we can plug in our expression for t1 plus t2, the total time. And so really what we're doing is we're taking the derivative of this expression and setting it equal to 0. So here's our equation, and we can take the derivative of the first term. v1 is a constant, so it can come out. It doesn't depend on z. And now we're left with the derivative of the square root of x squared plus z squared. We can use the chain rule. The derivative of a square root of x squared plus z squared is equal to 2z over 2 times the square root of x squared plus z squared. And similarly, we can find the derivative of the second term. It looks pretty similar. Now note that we have 2's in the numerators and the denominators of each of these terms, so they'll cancel. And we can move this, everything to the right of the minus sign, over to the other side, leaving us with 1 over v1 times z over the square root of x squared plus z squared equals 1 over v2 times d minus z over the square root of y squared plus d minus z squared. Okay, so here's our current expression. We're going to simplify this by first drawing in the normal. Notice we don't have any theta 1s and theta 2s which appear in Snell's law, so we're going to try to get those into our equation now. So we've drawn in the normal line as the dashed line, and theta 1 here, the angle between the light ray and the normal, is now labeled in red. And here's theta 2. And we can draw in those angles again using alternate interior angles, and we can see that the sine of theta 1 in the blue region is equal to the sine is the opposite over the hypotenuse, so it's the sine of theta 1 is z over the square root of x squared plus z squared. And similarly, the sine of theta 2 is equal to the opposite over the hypotenuse, or d minus z, over the square root of y squared plus d minus z squared. And now we can plug in these relations for sine theta 1 and sine theta 2 into the above equation, leaving us with sine theta 1 over v1 equals sine theta 2 over v2. Well, let's talk about our definitions for the index of refraction. N1 is defined as being the ratio between the speed of light in the medium, v1, and the speed of light in vacuum, c. So really we can define N1 and N2 using these equations that v1 equals c over N1 and v2 equals c over N2. And now we can plug these into our relation, leaving us with N1 sine theta 1 over c equals N2 sine theta 2 over c. And now the c's cancel out, leaving us with Snell's law. N1 sine theta 1 equals N2 sine theta 2.